We can use for loops to code up a scalar-vector multiplication operation. Let's look at two different representations. On the left, we see a mathematical definition, and on the right, we see some pseudocode to implement that definition in computer language. Let's read the first one on the left-hand side, and we'll call this scalar-column-vector multiplication. If we let alpha be an element of the real numbers, that means alpha is a scalar, and then x be an element of Rm times 1, that means x is a column vector with m rows and 1 columns, then we define scalar column vector multiplication as the vector alpha times x, which if we think about x as having m rows, that's alpha times individual scalar entries x1, x2, all the way down to xm. And we say that the scalar vector multiplication is just to bring the scalar inside each entry. So that becomes alpha times x1 in entry 1, alpha times x2 in entry 2, all the way down to alpha times xm in entry m. In other words, the ith coefficient of the output, alpha times x, is going to be alpha times xi, and that's for all entries. One thing that we're working on is to get your intuition running on how to use loops. Notice that there is a fixed number of operations that happens the number of times that we already know, which is the number of rows. And in the background, anytime we're doing the same thing over and over and over again with a fixed number of entries, we might be thinking for loops, right? For loops are same iteration for a fixed number of times, same operation. So specifically, let's kick over to the algorithm in pseudocode. We say for I goes from 1 to m. Remember in my class when I'm thinking about rows, I'm going to use the index I. And then also the row dimension is going to be m. So we run through each entry of the output vector y. So the ith entry of the output vector y is going to be alpha times the ith entry of the input vector x. We do that m number of times, so they get all the way down to the end of the vectors, and then we drop out of our for loop. Let's continue our trend of testing pseudocode using sandbox scripts. So I just created a new script. Let me go ahead and save this. This is going to be in my Engineering 11 Lesson 4 sandbox file. This isn't going to be a dot product algorithm. This is going to be a scalar vector mult algorithm. So what we need is a few different vectors. We're going to set x to be, let's call it all ones again. And I suppose we're going to say that there are m rows and 1 column. And then in this case, why don't we just go ahead and set m equal to 5. So we'll have 5 rows. And then y, we should initialize as zeros. And that's because one of the habits I like to do is if I'm going to define a variable, go ahead and create it before I work with it. So inside this, I'm going to set the ith entry equal to alpha times the ith entry of x, but I want to create that before I actually do that. It's kind of a old school thing. So I'll call this the initialization. And then let's go ahead and drop into our for loop. So this is for 1. I goes from 1 to m. And then what we're going to do is overwrite the current value of I, which is initialized to be 0, with the scalar alpha times the corresponding entry in the vector x. Of course, I should get an alpha scalar, so let's go ahead and do alpha. I'm digging the number 16 right now, 2 to the 4th. So now I have alpha, I have x, I have y, and of course the row index, I'm going down rows, and that's only because these are column vectors. So if this was a row vector, we would have to change that. All right, so I think I have it. Let's go ahead and do two things. We'll call ymat, that's going to be MATLAB's version of this, and that's going to be alpha times x. So the multiplication actually implements this operation. This is a very, very smart symbol in MATLAB. We can use it for many different purposes. And then we're going to call, we're going to compare the values of ymat with our values. So let's go ahead and run this and see what happens. And ymat is going to be MATLAB's version, and yes, I did mean. And then let's check our version, all 16s. If we look at the difference between the two of them, we say that the vectors are the same only if the entries correlate, which means those would be all zeros. So indeed, this algorithm produces the same thing that MATLAB's multiplication does. To do that, we're going to use this kind of structure. On the left-hand side is the algorithm that we coded up in MATLAB. It's not production level code. This is literally just pseudocode to get our head around what's going on with this operation. On the right-hand side is a series of visuals to represent what we've done in this code. So here is the math equation. We've got y equals alpha times x, that's scalar vector multiplication. On the left-hand side, we have our pseudocode, our algorithm to run this, which is for I goes from 1 to m, assuming both of these are m by 1 vectors. We set the ith entry of y equal to alpha times the ith entry of x, where this is the assignment operator. The visual progression, let's kind of think about this. Here we had a 5 by 1 vector. So we think about initialization. In initialization, we had already defined x. Here it is. We had already defined alpha. So that those two things are sitting in memory. In this case, these are all 1s, and this is 16. And then y we initialize to be all 0s. And the idea is we're going to overwrite the value of y with previous values of y. And this comes from, I used to code in C. And in C, we have to initialize variables before we use them. There is a way to dynamically allocate energy, memory. But for me, if I'm going to overwrite those values, I want them all sitting in memory. So that's what we've done up through line 4 of our code. Literally, we've set into memory 5 by 1 vector x, a single scalar alpha, and then a matching dimensions vector y, which is 5 by 1 with all 0 entries. So now we kick into the for loop in line 5. And the first thing we do in the for loop is set I equal to 1. And then what we do is we actually progress and set the first entry of the all 0 vectors equal to alpha times the first entry of x. So here we access memory to get alpha, we access memory to get x1, and then we overwrite the value sitting in y1, which was 0, with alpha times x1. So we see that that kicks. That drops us down to this. We check, are there any entries left? In other words, have we run through all of the indices? We have not, because we're going from 1 up to m. So I updates to 2. When I updates to 2, we go to the second loop iteration. We overwrite the second value of y with alpha times the second value of x. Again, there's a memory call here because we need alpha. We also need to go into memory to get x2. And of course, we're going to go into memory because we have a second vector. We're going to overwrite that value in the second position. And we just continue through. We go to the next iteration, fourth iteration, fifth iteration. Each time we're accessing memory to get alpha, to get the entry here, and to overwrite the entry here. And once we're done, we see that we haven't changed the vector x in memory. We haven't changed the vector alpha in memory, but our vector y now has alpha times x for each individual entry there. And so the output vector y does hold what we want, which is exactly what we see in our test. MATLAB produces alpha times x. Underneath, somewhere in the guts of MATLAB's code, is the same code, maybe implemented at a little bit more advanced level, from the standpoint that MATLAB is an entire library of functions that a bunch of programmers use. So it's got to be written better than this for sure. But the fact of the matter is that the MATLAB output is identical to our output. Now that we've implemented that introductory level, I want to talk about one memory saving technique. This is an introductory class, and we're not going to develop super sophisticated ideas of how memory allocation works in modern day computation. The goal of this class is to give you a sense of how MATLAB syntax works, and also the connection between using MATLAB and coding up linear algebraic operations. However, one of the themes of using computers to implement linear algebra is to be smart about how we allocate memory. So at a very, very low level, every time we access memory, there's a cost associated with that. And there are some things that we can do in our code to decrease the cost of accessing memory. With that in mind, let's take a look at a slight adaptation of our pseudocode algorithm to implement scalar-vector multiplication. Notice in the first version of this, we created a new vector y and then overwrote each individual entry with alpha times x1. Thinking critically about what we want, generally we don't really care about saving the values of x necessarily. It may be the case we need it, but in the case that we're looking for the output alpha times x, we could think about the vector x in memory as a storage location upon which we can write the output. So specifically, we could modify our algorithm. So instead of overwriting a new vector y, we could take the old value of x, multiply it by alpha, and then write that output back into the same value. Of course, if we were to do this, we would literally change this algorithm. We would delete the initialization. We don't need that anymore. And then what we would do is overwrite the previous value with alpha times that value. So that would change. So in this case, maybe we call this thing the initialization. So if we run this again, one thing that I got to be a little careful of, remember that ymat is the MATLAB expected output, and that's alpha times x, but I'm updating x dynamically here. So if I want to test this, I should probably move this here. So this is what we're going to be called a verification vector. Verification vector. This is what we say is our expected output, calculated in a different way. So this is MATLAB's version of our expected output. And then the claim is, if this algorithm works, whatever is stored in x should be identical to this vector. So let's go ahead and run that. And then let's check ymat. And then let's check x. Notice those two vectors are identical, meaning that this memory saving technique, the idea of overwriting x with its same value, did produce what we expected. Let's visualize this again to kind of get our head around both the algorithm and then what the change is when instead of using another vector y, just overwriting the value into x. So the math equation is identical. We haven't done anything different. We're producing an output y, which is alpha times x. But the major difference is in how we code it. So here, we're not defining a new vector y in memory. We're actually overwriting each individual value of x with alpha times the previous value. And that's what this assignment operator. Remember, this is a computer science construct, not a mathematical construct. So the visual progression, when we initialize, we have the scalar alpha and the vector x, which is a 5x1. When we drop into iteration 1, we overwrite the first value of x with alpha times x, a single call to memory in the vector x. And then we do the same thing down, alpha times x2, alpha times x3, 4, 5. And then when we finish, we've now overwritten the previous value of x with alpha times each individual entry, and we've produced what we wanted. Challenge to you all is come up with an alternate definition that says scalar row vector multiplication. What is the definition that we would use mathematically? And then how do these two algorithms change? That's kind of entry-level community challenge. And then a more complex version of this is come up with some mental model that describes why this is a savings and why we might want to use this, because it does depart from the mathematics, right? This is one of the themes that we're going to see. There's math operations, pseudocode, and then algorithms to implement that pseudocode. And often in those algorithms, we use memory-saving techniques that don't really have anything to do with mathematics and have much more to do with how these computers that we're using are engineered to do math operations. With that, thank you so much for your attention, and we're going to move on to generalization of the scalar vector multiplication operation. See you in the next one.